Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Surface Drainage in Roads and Pedestrianised Zones. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, ACO. ACO in Australia offers an extensive portfolio of stormwater, building drainage systems, cable pit and ducting systems, access covers and other niche products. The company was established in 1933 as Australia's foremost manufacturer with facilities in Western Sydney, New South Wales. ACO takes pride in providing excellent customer service and extensive technical support from specification to the finished product installation. Today, we will hear from two speakers, followed by a live audience Q&A, and encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Colin Leake. Colin has over 40 years of experience in the engineering field and holds various positions and titles amongst many prestigious institutes and networks around Australia. In addition to being an engineer, Colin also teaches as an adjunct professor at the University of Western Australia, lecturing in pavement engineering, and is engaged in mentoring PhD and final year students undertaking their research-based projects. Colin has been the champion for in situ foamed bitumen stabilisation research and development, recycled material in road construction, a prime mover in the adoption of responsible stormwater management, as well as being recognised for his environmental awareness and assistance to community groups in constructed wetland developments. Please welcome Colin Leake.
Thanks, Amanda. Well, this presentation is on surface water of roads. It's not a full stormwater presentation. It's purely about getting rid of the surface water on roads and some of the issues that we have with surface water. Our aim with surface water drainage is basically very simple. We just want to remove that excess water from the road surface, generally following a rain event, although it can be a burst water main. And we want to drain that into a drainage system in a controlled manner as quickly and effectively as possible. The outcome is a wet but dry road or pathway, but the problem we have is that we do have contaminated runoff. This has been something that's concerned me for a long time, is where does all the rubber from the tyres go? And if you do a little bit of research, you can find that the average life of a passenger vehicle tyre is 40,000 kilometres. And for a heavy vehicle, it depends. If it's a long haul on a rural road, and mostly that's not too much of a drainage problem, you can get 200,000 kilometres out of a set of tyres. But around urban areas, about 50,000 kilometres is considered about normal. And the average rubber loss of those tyres for a passenger vehicle, it's about 1.2 kilograms. For a heavy vehicle, 12.6 kilos. And on a reasonably heavy trafficked urban road, for example, with 10,000 vehicles per day with 10% heavy vehicles, that equates to about 1.12 tonnes per year per kilometre of granulated fine-grained rubber, which ends up in our stormwater systems. So our surface runoff contains from roads, it'll contain rainfall, and we've got to recognise that with atmospheric pollution, that might not be the pure water that we dream of. That rubber that I previously spoke about, hydrocarbon spillages, exhaust particles, organic matters from vegetation that lines the road or leaf matter that falls onto the road, not to mention dead animals. We've got fertilisers, herbicides and pesticides that might run off from curb spraying activities or spraying on verges. And then you've got the cigarette butts and other flotsam that comes from us humans, reputed to be the highest form of life, but sometimes I think that's debatable when I see what's in the stormwater systems. In pedestrian areas, we're going to have all of the above, except probably the hydrocarbons, exhaust particles and rubber. So when we're looking at surface water runoff, the first thing we've got to do is get rid of the volume of flow. And that's going to depend on the recurrence interval we design for. And that recurrence interval is going to give the storm intensity that we're considering, whether it's using the old term, a 1 in 2 year event, a 1 in 5 year event, 1 in 10 year, and so on. And having known the recurrence interval, then we need to know something about the flow paths, where that water is going to run, and the width of flow. And that width of flow is going to depend on the geometry of your road. Then we've got the method of removal, how we're going to get rid of that water from the road surface. But as I call it, what are we going to do with that soup? That stuff that I'd call soup, but we certainly wouldn't want to eat it or drink it. So the removal from roads is dependent on the crossfall, which again is related to the pavement type. So in this presentation, we're probably more concerned about curb type roads, but in rural applications, that crossfall is going to be increased depending on whether it's a spray seal or a gravel surface or a natural earth surface, and we want to get rid of that water into the table drains. But where we've got curbs, we need to have catch pits, and those catch pit types will determine the spacing of how far apart we need them. With a steep longitudinal fall, then we're going to have high velocity, which is going to mean a relatively low flow width. When the road longitudinal grade is pretty small, and around where I am, 0.5% is sometimes difficult to get. We've got to introduce that sort of longitudinal grade. Then you need a crossfall, a relatively good crossfall, to confine that water as close as possible to the curb. You don't want it getting out into the wheel paths of the roads, mostly because that water can cause safety issues as far as stability of the vehicle goes. But the other issue you have is that vehicles driving along the road in congested areas, if it's in the width of flow, will cause massive amounts of water to be flicked up onto the footpath and any unfortunate pedestrians that happen to be there. In pedestrian zones, we're still interested in the flow paths, grades and catch pits, but the type of catch pit we need needs to be different to what we would have in a road. There is a tendency towards water-sensitive urban design options, and there's a number of examples here where we've got street gardens or tree pits where water can drain off the road, go through these devices, and if you're in a very free draining subgrade, then these might be sufficient on their own to get rid of the water. But if you're in a clay soil, then you might need a subsoil system underneath these to drain the water out. But if you've got a good filter medium where these plants are planted, then you can actively control the discharge of water through a subsoil system. You can have all different types of these. The other type, as you see in this centre bottom photograph here, is permeable paving. where rainfall falls onto the paving, and in this case there's spaces between the bricks, which is filled with a permeable material which allows the water to soak through. Or other examples are no fines concrete, where the whole block paver is permeable and water can run straight through the block paver and down into the subgrade. And indeed, the same can be achieved with open grade asphalt, providing you've got a free draining base and sub base. However, it's important to get the drainage right. This example here is a case of urban sensitive water design, where the table drain wasn't deep enough and the control of water was sitting in this drain. It wasn't longitudinally drained sufficiently. It actually drained into the groundwater with soak wells, and the groundwater level was high. And the result was, as you can see in this photograph, that there's massive fatigue failing of this particular pavement. So when you're designing a water-sensitive urban design, it's most important to recognise that we do need a pavement that survives. And that's particularly important because we're trying to be environmentally sensitive, and if we've got roads which only last a short period of time and we need to plonk more and more asphalt on to keep repairing that particular road, then that's a consistent source of greenhouse gas generations that the environment can certainly do without. So where does all that soup go? Well, the old way we used to do it, we used to pipe it to the nearest watercourse. And in doing so, we let the wildlife deal with it. And if you were a turtle or a fish or something like that, then maybe you could deal with it. But we humans wouldn't tolerate it. And why should we allow the wildlife or impose it on the wildlife to deal with? So the new way, and the first and foremost, is that we must regularly street sweep those streets. Get all that rubber and debris and flotsam off the road and do it regularly. That's the first and best form of treatment for surface water runoff from roads that you can do. We can have gross pollutant traps. Trouble with gross pollutant traps is that they're generally underground and they need maintenance. And all too often, these things will be installed. They're out of sight, out of mind, and people forget to maintain them. We can have gully filters or gully traps. Filters are a method where we can have some high flow fabric that's got small opening size that traps the fine particles and any debris, but allows the water to pass through. Again, they need maintenance. Where I used to work, we used gully traps. That was what we call a square, sort of like a T-piece on the outlet going into the pipe system, and that T-piece was aimed to skim off any surface pollutions, or it allowed the sediment to build up in the bottom of the gully because it's well and truly below the outlet pipe, and sediment could be retained in that gully. But again, maintenance was important, and those gullies need to be cleaned out regularly. We have retention and detention systems, and I've got an example here of one of the many that I've used in the past, where these chambers are inserted into the ground. It can be in a park, can be under roads. I've installed a lot of these under the road surface, and these are designed to either retain or detain, or a combination of both. In a retention system, there's no outfall. In a detention system, you might have an outfall pipe of much smaller capacity than the infall pipe, so that the the volume of flow is retained in these systems. What is important with these systems, and in this case, they're connected via holes in the side of the chambers, and they're surrounded by aggregate, and that aggregate allows water to flow from one to the other. So in the case when I build them anyway, I put an access chamber in one of those chambers, and that access chamber then becomes the cleaning access for getting rid of any debris that might settle out in that primary receival chamber. The other chambers are filtered anyway, so it's very unlikely that they're going to pose a problem with siltation or anything like that. The other thing we can do is we can have constructed wetlands. And these are just some examples that I've been involved in the past. These are constructed wetlands that are around the city of Canning, various methods. And believe me, the flotsam that comes off roads can be devastating to these. What we did find in the early days with one of the in particular is that there was so much pollution coming through that the reed matter that we planted died. It was permanently inundated. And we found we had to go and backfill it so that in periods of flow we could turn parts of the system off so to be exposed to the atmosphere, and the sunlight would then burn off the pollution. By doing that, we managed to get the macrophytes to grow. Open drains too. Sometimes we have water that will discharge into open drains. And on the top here, we've got an example of a trapezoidal drain, which engineers seem to love. And it is to my shame now that back in my early days of my career in the very early 1970s, working with a public works department in Western Australia, we would go to a perfectly beautiful little stream. As engineers, we would decide that we could make it flow more efficiently to carry water away quicker. So we'd turn that beautiful little stream, that living habitat, into a dead trapezoidal drain, which did nothing but carry water, carried it fast, and certainly achieved the drainage requirements, but wasn't good for the environment. That particular one on the left, what we did is we went back to it years later, and after a lot of work, we converted it into what we call a living stream, which is the right way to build a trapezoidal drain. And interestingly enough, the property values for those locations adjoining this living stream skyrocketed. They now had something that was really beautiful, a natural environment. We had drop structures or riffle structures in it that kids love to play in. They'd come down and play in it. It cleaned the water up, and there's now turtles and other aquatic species in that living stream. However, I do have a question for the environmentalists that might be amongst the audience. That's a question I've raised but never had an answer that someone can answer. In Western Australia, all of the major rivers into the Swan River have been dammed. We've got decreasing rainfall. The river flow has dropped by 75% into those dams, so the dams never overflow. My question is, should the stormwater still be retained at source, which is what urban sensitive water design states we should be doing, or should it be cleaned and diverted back into the rivers to restore some of that flow that is no longer there? The other thing that we do have when we've got these stormwater systems is we will have pits in road. And what I have noticed is at one stage you used to be able to buy Gatic covers. The Gatic was a trade name. They were Australian made. You could put them in a road and they would last for decades. I've got these in existence that were Australian made that have been surviving for 50 years. Unfortunately, importers got on the bandwagon with stuff from China and India, which didn't have the lifespan. They rattle and bang and lose stability. Once they start to rattle, then the impact forces breaks the bedding. They become unstable and they're a never-ending maintenance item. The other thing is the lost skill in people able to get these to a level that doesn't disturb adjoining residences. And the past skills, you could drive across one of those and not notice it. This one has had at least 4 goes at trying to get it level so that it didn't disrupt adjoining residents with noise, but to no avail, still noisy. The catch pits we have, these are the typical ones that you'll see. There's the old grated cast iron ones. They're in the left there, the top left. Very unpleasant for cyclists and block easily. You can get more cycle-friendly one, as the one on the bottom left is. But again, while it's more cycle-friendly, they do block easily. We can have the straight side entry on the bottom. Far easier on cyclists, particularly if you offset them back a little bit more so that the diversion flukes are not in the cyclist ways. Or you can have the combination side entry gully, which is on the centre top. And advantage of the side entry is that they don't block as easily. So you can get rid of the stormwater certainly quick enough. But the issue you do have is that the pollution or the debris gets down into the system far more easily, which means gross pollutant traps have to work harder. Because the issue with all of the grated ones is that every time you do a resurface, you've got to either raise the gully, or if you keep the road level the same, you've got to work your way around those gullies to match the particular gullies. So you've got to profile out your asphalt to make it level again, which is much easier to deal with as a side entry gully. However, you need to design the spacing of these so that the flow width is not excessive. On the top right here, you can see what happens with a grated gully in high flows. You'll get splash over. And if the water's fast enough, it can some of that water can splash right over that gully. And the bottom right example is a good example of how we have to design. It's basically designed as a broad-crested weir to get the volume of water into the gully. Pedestrian catch pits, much emphasis must be placed on pedestrian safety. We need to have heel-safe grates so that pedestrian heels don't get caught up in them, but they still need to be efficient to drain the water off. The bottom right is an example of a slot between bricks. I haven't found that a particularly effective way, unless you've got a good pipe system underneath to drain the water away. So that's it, guys. The references for those items on rubber, if you're interested, are shown here. So thank you very much for listening.
Thank you, Colin, for a great presentation. I'm also delighted today to announce that ACCO will be offering a prize to one of our attendees today. The prize will be announced on the ACCO LinkedIn page and will go to the best answer of the following question. What is the best way to optimise the hydraulic efficiency of a trench drain? Please send your answers to the email on your screen, which is also in the description box. Entries close Wednesday, the 27th of September at 5 p.m. Australian Eastern Standard Time. Good luck. I'd now like to welcome our second speaker, Darren Chan. Darren is the brand manager at ACCO for civil construction products and the authorised representative for ACCO's testing laboratory at the National Association of Testing Authorities, Australia. At ACCO, Darren continues to support engineers and designers with innovative products and free online design tools. Please welcome Darren Chan.
Good afternoon, everyone. My name is Darren Chan, and I am the Product Manager for ACCO Civil Construction Products. Before I go on, I want to thank Engineers Australia for hosting this webinar and to Colin Leake for an excellent presentation. So today, we're going to look at surface drainage in roads and shared spaces. We will begin with surface drainage for roads. Looking at modern road drainage designs, we have a lot of challenges from our growing population. So as our population grows and cities become more and more densely populated, engineers are being tasked with designing effective road networks and integrating drains and other services in narrower and narrower road corridors, either to widen or reconfigure existing roads or to extend or add lanes for turning bays at intersections. Beyond just trying to fit more into a smaller space, other challenges include connecting into an existing stormwater system that can't cope with the increased flows from new developments, and trying to avoid clashes with underground services. The primary objective of road drainage is to ensure the safety of all road users, whether it be motorists, pedestrians, or cyclists, by reducing the depth and width of flow, managing, reducing, or eliminating sheet flow and the spread of gutter flow will minimise the risk of hydroplaning and vehicles losing control, and slips, trips, and falls from pedestrians as well. Surface runoff on roads is collected and channeled along curbs and gutters and medians on super elevated roads. Inlet structures are used to capture surface water and transfer it to underground pipe systems. This could be at a sag point to prevent ponding, on grades before the water depth, width, and velocity becomes a hazard, at approaches to intersections, upstream of pedestrian crossings, and at bus stops where people congregate. There are three traditional types of road drainage inlets available: side entry inlets through openings in the curb face, graded gully pits positioned in the gutter, or a combination of the two with an extended side entry. You can also capture water continuously rather than intermittently, using either graded trench drains or curb drains. These would be used in areas that are very flat with minimal fall, or have services in the ground close to the surface. These continuous capture systems are more cost-effective solutions than installing closely spaced traditional curb inlet pits and deep pipework. Austroads released a guide to road design with an expanded drainage section in 2013. It was written with a consortium of all the state road authorities. Since this document was published, continuous capture inlet systems have become a more accepted method of draining road pavements in certain applications. Let's focus now on continuous capture inlet systems. Graded trench drains are one type of continuous capture inlets. Due to the rainfall variance in Australia, 200mm or 300mm wide channels are commonly specified as they are compact with variable depths to ensure the runoff is discharged efficiently. There are generally three types of grades: high flow with large apertures, hill safe for pedestrian safety, and transverse slotted grades. Grades must be load rated to AS 3996 Class D and preferably fitted with boltless locking mechanisms that allows quick access for maintenance to clean out the trench drain from time to time. Precast polymer concrete channels have a very smooth surface and are available with built-in slopes to remove water effectively from flat areas. Hydraulically, a V-shaped profile channel creates higher velocities during low flows compared to a U-shaped or flat-based channel. This is due to the narrower V shape at the bottom of the channel, which creates higher velocities to prevent self-cleansing to help keep the channel clear of debris and silt. In precast channels, the V-shaped profile creates deep pockets in the side walls of the channel, which allows the concrete encasement to mechanically key in the channel for a strong installation. Channels with ductile iron edge rail rather than steel edge rail provide a more durable solution. Edge rails with anti-shunt lugs will prevent longitudinal movement of the grades. There are many ways to install precast channels. One way is to use installation devices. Installation devices clamp the channels together to prevent movement and floating during concreting. They make installation quick and easy and with a single concrete pour. High flow grades have large high capacity inlet slots. This allows the runoff to be quickly intercepted and removed from the road. These large intakes also minimize the risk of grades blocking up and spreading the flow into the traffic, creating hazards to motorists. Even though these grates have large apertures, they are bicycle compliant to AEST 3996, which means bike tyres are unlikely to get stuck in a grate causing injuries to the cyclist. These large apertures allow the channels to be cleaned without removing the grates. A sucker truck with a high pressure washer is used to break up the sediment and wash it down to the vacuum pump, which sucks up all the suspended silt into the truck. All this can be done without unlocking and removing any of the grates. Another type of continuous capture inlet system is the curb drain. This product combines two functions, the drainage channel with the curb itself. It's a shallow solution that requires less excavation for the installation, therefore less likelihood of clashes with existing underground services. Options include semi-mountable and barrier type curb profiles, depending on the specific area within the roadway. There are narrow 100mm wide curb drains which are ideal for minor roads in council areas and is a good compact size for smaller catchments. The 200mm wide curb drains are for major roads and larger catchments. Semi-mountable curb drains are used in medians predominantly. The barrier curb drain is the non-mountable option that is used adjacent to footpaths. Precast curb drain channels are encased in concrete and tested to AEST 3996 Class D loads. Access units are required at regular intervals, say every 20 to 30 metres, to provide access for cleaning and maintenance. And here I'm just going to quickly run through some installation examples of where graded trench drains and curb drains have been used on different parts of roads and highways. So for medians, they might be used to eliminate the spread of gutter flow into the traffic lanes by continuously capturing the water rather than traditional pit and pipe construction. Curb drain is a smaller system, so depending on the hydraulic capacity requirements of the project, wider and deeper graded trench drains might be a better option. For right-hand turn bays where you're trying to fit more lanes into a smaller area, curb drain can be a helpful solution to give as much space to the roadway as possible. Some engineers and road authorities may prefer graded trench drains to curb drains in this application. And in curbside gutters where existing inlet pits are spaced too far apart, resulting in hazardous spread of flow, curb drain can be used to continuously capture the gutter flow to minimise the risk to motorists. Or again, a graded trench drain solution can be used. Curb drain can be used to intercept water upstream of low-lying properties to prevent damage to buildings and inconvenience to workplaces or residents. And likewise, graded trench drains can also be used. And on bridge abutments and tunnel portals, you can again use curb drains or a graded trench drain solution. Bus stops and railway interchanges are areas where we have a lot of commuters, and during storms we don't want anyone to get splashed by motorists. So again, we can use curb drains to get the water off the road quickly, or a graded drain too. A big driver on every project is cost. Precast curb drains and graded trench drains are ideal for applications where curb inlet pits would otherwise be spaced closely together at intervals of 20 metres or less. It's more expensive to install pit and pipe in these applications than a graded trench drain. This is an example of a road project. The designers opted for closely spaced pits and pipe where a continuous capture inlet system would have been a more cost-effective solution. And we've carried out an installed cost analysis of a curb inlet pit and pipe system compared to a precast graded trench drain and curb drain system. The outcome was the graded trench drain was 15% cheaper than the pit and pipe, and the curb drain was 36% cheaper, so quite significant savings. Finally, for road drainage, precast channels can be installed on curbs. This can be done by opening up a gap on the inside or outside edge of the channel, or gentle curves on a larger radius, or by grinding and mitering the channel units on site for tight curves with a smaller radius. For example, on an intersection upgrade and widening project where Telstra services were clashing with the pit and pipe design, they designed and installed a shallow curved graded trench drain to act as a pipe to move the runoff around the corner of an intersection to discharge into an existing curb inlet pit, which avoided clashing with the existing underground Telstra infrastructure or the need for the costly relocation of these services. We will now look at shared spaces and the important considerations to correctly specify and integrate a surface drainage system that is safe for both pedestrians and motorists. Shared spaces are increasingly transforming city centres, transport hubs, and public domains into an inviting space where it is accessible to all users. This is how Austroads describes shared spaces, or a shared zone. A shared zone in an area utilised by both pedestrians and vehicular traffic, in which drivers must give way to pedestrians at all times and where the street environment has been adapted for very low-speed vehicles. Shared zones are normally used in areas of high commercial activity, medium to high density residential areas, or recreational areas. Ideally, shared spaces are located in areas with relatively flat pavements, and a surface drainage needs to be designed with an appreciation of the great slot sizes, slip resistance, loading, durability, and must be accessible for the safe passage for both pedestrians and motorists. Arup recently released a report that lists 50 benefits associated with making cities more walkable, with improvements from mental health to a sense of belonging, accessibility, and supporting local businesses. As younger generations move away from driving, the importance of pedestrian areas in our cities will only increase further. Jeff Speck, who wrote the Arup report on walkable cities, said, "Get walkability right and so much of the rest will follow." So creating these walkable cities leads to all these community benefits and creating spaces that people want to be in. There are many other reasons driving the importance of shared spaces, and whilst urban designers must consider many stakeholders, the needs of pedestrians should come first. The risk of slips, trips, and falls in poorly designed pedestrian areas is high, and the legal consequences of these accidents can be quite extreme. And with $500 million of injury claims in Australia in 2020, this is a significant cost and risk that we need our designs to help mitigate. So with any application or product, compliance with relevant legislation and standards is vital and will help solve many of these problems. When it comes to pedestrian safety for pavement elements, the requirements are spread through a number of Australian standards because of the multitude of factors that need to be considered. So we'll look at those standards in more detail shortly. And in addition to Australian standards, many councils have their own planning regulations, particularly when it comes to streetscapes. If there are no applicable Australian standards, European or other standards are referenced. The following are some examples of roads transformed into shared spaces. This is a before and after shot of Bank Street in Adelaide, which was transformed into a shared space, where the speed was dropped to 10 kilometres per hour and the curbs removed so people can move freely and share the space with vehicles and bicycles alike. George Street in Sydney has been converted into a shared zone, with pedestrians, trams and vehicles accessing buildings. A flat space was created with the removal of curbs and gutters. Graded trench drains and specially designed tram drains were used extensively throughout the light rail corridor. Bundah Street in Canberra is a commercial and shopping precinct, with shared zones created where vehicles give way to pedestrians at designated raised road crossings. Graded trench drains were used to outline the extent of the road and to intercept runoff from the pedestrian areas. Victorian projects where curbs and gutters are removed and replaced with graded trench drains to allow pedestrians to move in all directions in that space. Some South Australian examples of graded trench drains incorporated into nicely paved pedestrian-friendly areas that are accessible by motorists. In the Hobart Airport project, a trafficable graded trench drain is used with different pavers and bollards to clearly segregate the shared zone and pedestrian-only areas. Some Queensland examples of shared spaces in an education precinct and medium to high density residential area. We will now look at some key factors to consider when designing a drainage system in a shared space. Here are the 5 key considerations when integrating drains into pavements to achieve those objectives of safety, form and function. And that's flat drainable surfaces, slot criteria, slip resistance, durability and strength, and access for maintenance. Then we will discuss how drainage in shared space will integrate with other transport modes and discuss hydraulic performance, as it's a critical factor. Uneven or steep pedestrian spaces will create trip hazards, particularly for the elderly, children, and those with a disability. Surface water management often leads designers to create steep pavements, but they can be designed flat if drainage is properly considered and incorporated during planning. Graded trench drainage systems are continuous capture inlets with simple constant grading on both sides of the drains. As discussed earlier, precast drainage channels with a V-shaped profile have hydraulic advantages over U-shaped channels, in particular during low flows with higher velocities. For pavements that are flat, channels are available with built-in slopes in the channel invert, providing internal fall to promote efficient drainage. Precast trench drainage systems are quick and easy to install, particularly compared to cast in situ drainage. The next element to consider are slot sizes. Slot sizes are critical for pedestrian safety and should also not hinder accessibility for wheelchairs and walking canes. New building works must be designed to comply with the Disability Discrimination Act. The DDA makes it against the law for public places to be inaccessible to people with a disability. Slot sizes of grades will also determine how safe it is for cyclists and pedestrians wearing high heels or stilettos. AEST 1428.1, Designed for Access and Mobility, was revised and released in 2021. Clause 4.4 states the following. Grates in paths of travel shall be in accordance with the following. A. Circular openings shall be not greater than 13 mm in diameter. B. Slotted openings shall be not greater than 13 mm wide and not greater than 150 mm long and be oriented so that the long dimension is transverse to the dominant direction of travel. C. Linear openings shall be oriented so that the longer dimension is transverse to the dominant direction of travel, except where linear openings are less than 8 mm wide. Where linear openings are less than 8 mm wide, orientation is optional. Bicycle safety is mandated by AEST 3996, which takes into account the type of bar used in a grade and the maximum slot dimensions to stop bicycle tyres getting wedged in the grade. Hill safety is one of the most common complaints from users. Whilst there is no Australian standard for hill safety, there is an American standard that calls for slots less than 8mm. There's a trade-off here between hydraulic intake and hill safety. So we don't want to see very narrow gaps that, whilst they are hill safe, they don't actually collect much runoff and it is more prone to blocking up. As a result, we lean to a guideline of 10mm. Slip resistance is becoming a major concern for asset owners as litigation increases arising from slips, trips and falls. AS 4586 with a supporting handbook HB 198 stipulates the slip resistance ratings for a variety of applications. AS 4586 outlines 3 test methods to simulate different applications as a means to assess the slip resistance of a grade. The all-wet ramp with ratings of R9 to R13 is designed for industrial and commercial environments where there is likely to be oil on the floor, for example in workshops and commercial kitchens. The wet barefoot test with ratings of A, B and C is designed for wet areas with bare feet such as pools or change rooms. Lastly, the wet pendulum test with ratings of P0 to P5 is the most widely used test. This test is most suited to areas that are rain affected, such as shared spaces and building entries. Next up is loading, and considering the anticipated vehicle load that a drain will be subjected to is critical. Underestimating this can lead to product failures, and overestimating it adds unnecessary costs. Load isn't just related to the physical load of the vehicle, we must also consider the type and speed of vehicles, the wheel load, how the vehicle will move over the grade, and the number of movements. AS 3996 is the Australian standard for access covers and grades. This standard provides a means to test a grade to determine the load classification, but it doesn't take into account the underlying drainage structure. However, EN 1433 is a European equivalent, and it includes testing for the drainage channel. This table looks at the load classes specified in AS 3996. It classifies applications for pedestrians, load class A, all the way up to aircraft pavements, load class G. Shared spaces will fall into load class C. Malls and pedestrian areas open to slow-moving commercial vehicles. Road drainage to be specified as load class D for major roads, freeway shoulders and loading docks. If grates aren't locked into the channel, it can damage both the channel and the grade. A boltless locking system on grates are quick and easy to use to gain access for cleaning. The other option is bolted grates, which has the risk of the bolts vibrating loose during service. It's also common to see bolts removed during maintenance but aren't secured back in place, causing safety risk and hazard for loose or misplaced grates. Slot drains require discrete access points that help preserve the visual continuity of the pavement. Access points are installed at the start and end of every run and every 20 metres or so throughout to provide access for maintenance. With state governments all over the country investing billions of dollars into public transport, new metro lines and light rail projects are connecting commuters from their place of residence to city centres, transport hubs, hospitals, tertiary institutions and entertainment precincts, creating shared spaces in and around each of the stations. Light rail systems have been established in many cities and new lines are constantly being designed and delivered. Light rail, more so than metro lines, run on the surface and are incorporated into shared spaces through high pedestrian trafficked areas. Designers are challenged to provide an effective drainage solution in very flat areas with the complexity of draining the track rail grooves. Specially designed tram drains will discharge the flow from the track rail groove through the holes drilled into the rail into a chute connected to a trench drain and a pipe system. The chutes are made from rubber and is also used to isolate any stray currents from the track rails, potentially making the grates live and hazardous to pedestrians. Tram drain grates should be designed to take into consideration the 5 key factors discussed earlier. Absolutely critical to selecting a drainage system is the hydraulic performance and whether it will do what we need it to do. The hydraulic performance refers to the amount of water a drain collects in a given period of time, and that drives the product selection not only for the channel, but also the grate, as the grate in some cases can be the restricting factor. An undersized drainage system can increase the risk of hazards and damage to property if the flows are not captured. But conversely, an oversized system just adds unnecessary cost into a project. So how to get this right? The science behind the hydraulics of a trench drainage is complicated, and there are many theories and equations to calculate it. It is common for designers to use simple pipe or open channel theory as a means to calculate drainage capacity. However, this assumes that the flow in the channel is uniform. This might work for a culvert or for a pipe where liquid moves from one end to the other. Non-uniform flow is a more accurate way to model a trench drain's hydraulic performance, as it takes into consideration the collection of flow along the length of the trench drain, which is used to plot the changing water profile within the trench drain. Beyond the channel, the grate is the other consideration. Typically, the channel will reach its hydraulic capacity before the grate, but depending on the style of the grate, it may not be capable of capturing all the flow, even if the channel is sized correctly. A grate failure is categorized by the water bypassing the grate, as shown in the bottom image. Beyond the pure grate intake area, which is the open area of the grate, there are other factors that influence grate hydraulics, including the slot size and orientation. The number of slots and the raised slip-resistant nodules also impact the flow of the water, as they slow the flow down and helps direct the water into the slots. And lastly, just to touch on a bit about ACCO, just in case you're hearing about the company for the first time today. ACCO in Australia was established in 1994. Over the years, ACCO has expanded beyond polymer concrete channel and pit production, and now manufactures stainless steel trench drains, rotationally moulded plastic pits, mild steel fabricated access covers from our head office at Emu Plains in Western Sydney. ACCO product brands include ACCO Drain, our range of architectural and commercial trench drains manufactured from polymer concrete with a wide selection of grades. ACCO Infrastructure is our drainage channel specifically designed for heavy transportation infrastructure applications. ACCO Storm Bricks are modular underground stormwater storage tanks for retention, detention, and infiltration. ACCO Access is a range of discrete access covers, and ACCO CableMate is our cable pit and cable ducting range. Developed in partnership with Engineers Australia, we have launched 2 white papers. The first is dedicated to understanding the hydraulics of trench drains. The other on the importance of proper surface water management for pedestrianised pavements. We will give you links in our post-event webinar this afternoon. ACCO can assist with your next project. We have do-it-yourself online programs that provide quick, instant answers for your preliminary design. Programs include Hydrolite, a trench hydraulic program used to size up or check the performance of your trench drain design. GIC is the grate intake calculator to show the performance of your preferred grate based on experimental test data. Scheduler can draw simple trench drain runs and provide layouts, long sections, and a bill of materials to assist in procuring and installing the products. During detailed design, you can contact ACCO's technical support team for an ACCO proposal with full hydraulic documentation, along with information to assist with your specification, such as general installation details, specification clauses, and product info. Lastly, just to reiterate that we are here to help with all of our products. AskACCO.com.au is how we capture all of the services that we offer. So you can head to this site to access the channel hydraulic service, grate intake calculator, and design request forms, and so on. Also, our websites contain a lot of information and downloads to assist with your next project. These are our technical representatives around Australia who are very happy to assist you with your project either remotely or face-to-face. We have two websites. The first is on commercial drainage in urban, public and commercial areas. The second is on specialist drainage for transportation corridors. A post-event email will be sent to you shortly containing all contact information. I want to take this opportunity to thank Engineers Australia and Colin Leake for presenting with us. Thank you so much for listening and attending today's webinar.
Thank you. Huge thank you to Colin Leake and Darren Chan for those great presentations. We're now going to do something a little bit different before we get into the Q&A. And we'd like you to, we'll be running 3 polling questions. So if you could use the Slido link in the description box below to participate. And we're asking the engineering profession 3 questions. The first one is, what grade inlet size would you deem acceptable in most public urban spaces? Second question, along a tight curbside gutter, if curb inlets pits cannot be accommodated, what is your linear drainage preference? And the third and last question is, what do you value from a drainage supplier? Rank 1 least important, with 5 being the most important. And thank you. All of these things just help us to shape how we move forward, and also with our industry partner. So a big thank you to everybody who's put forward questions today. Please keep those questions coming through the YouTube chat box. And thank you to everyone who sent through a question when they were registering. And we might start with some of those. So Darren, we have a question for you that's coming from Chark, and Chark is watching from Asia. So good afternoon to you, Chark. Asking Darren, what are the challenges about drainage design in roads? Big question, probably a webinar on its own, Darren.
Thanks, Chuck, for your question. There are many challenges, as I outlined in my presentation, in particular in metropolitan areas now, where there is we're trying to widen roads, introduce more lanes, more traffic to cater for more traffic. So we're trying to fit more into a smaller space, and we're confined by the built-up environment that's already there. So things like putting your road in itself, along with all the road barriers, including the drainage and all the things into a corridor. That is the biggest challenge. So for engineers, it's really trying to find that design to fit everything in, and trying to make it the most cost effective, and that's the challenge there. So with some of the products that I showed for road drainage, like the continuous capture inlets, the great I suppose advantage of those are they're shallow systems, and in built-up existing environments, you've got a lot of services in the ground, and those services have been in there for a long time, and to move those out of the roadway or to put in your drainage design is a very costly exercise. So trying to avoid relocating services, that would be a very cost-effective way to do it, using curb drains and graded trench drains, as they're shallow, so you don't have to dig all that up, move it away, and then put in your drainage system. In most cases, these road authorities allow you to build over the top of those, and those utilities allow you to build over those, and then you can put in a shallow drainage system. So, yeah, there is it is a challenge, and I'm sure you all know about it.
Thank you for that. Colin, just bringing you into the conversation, we've had a question coming from Mohammed, who's watching in New South Wales. Good afternoon to you, asking, Colin, do you think it's necessary to revise the current design standard vis-a-vis the Storm ARI for new developments in light of the recent flooding events? And what would be your estimate of the possible increase in cost, if it is? Thanks, Colin. I think Colin's having this sound, so I might just come back to you, Darren. And we have a question from Charles in Queensland asking you, Darren, how can we get transport authorities on board with adopting these systems? Thanks, Charles.
Yeah, good question. At ACO, overseas in the UK, curb drain has been very popular for over 25 years now. We tried to bring that into Australia 20 years ago, and we had some success with the former RTA. Had a few installations, and from then, I suppose it sort of snowballed. Designers saw the value in using these continuous capture inlet systems on roads, and especially in flat areas, and to avoid existing services. And then, as RMS adopted it in the rewriting of the AEST roads in 2013 by introducing an expanded drainage section, we were able to discuss with RMS and a few other road authorities, and they put those continuous capture inlets into AEST roads, and then from there, it went from there. So with our products, we've actually got a product approved with the New South Wales Department of Transport. So the curb drain and the traffic drain is actually an approved product, and it's actually on their website. The Department of Main Roads there, Transport and Main Roads. We helped develop their technical note on trench drains, TN 162, which includes graded trench drains in roads. And with MRWA, we actually developed a curb drain to meet the curb drain profile of the semi-mountable curbs to fit seamlessly against their standard curbs over there. And we've had a lot of success in Vic Roads and Department of Infrastructure and Transport in South Australia and all the other territories. So if you go to our website at acoinfrastructure.com.au, you can have a look at our case studies, and you can see many examples of where graded trench drains have been used and curb drains in both medians and along the shoulders of roads.
Thank you for that, Darren. I might just come back to Mohammed's question now that Colin's audio is good. And Colin, Mohammed was asking, do you think it's necessary to revise the current design standards for the storm ARI for new developments in the light of the recent flooding events? And what would be your estimate of the possible increase in costs with that? Colin.
Yes, okay. Well, that's a pretty difficult question. Even in Perth, with the drying climate that we have, the intensity of storms or more intensive storms are happening more frequently. So yes, there is a requirement, I think, to upgrade the rainfall intensity values that we use. However, with the floods that you've had over east, no drainage system is going to cater for that. When the major rivers are flooded, your drainage outlets are flooded, you're not going to get any more water into a flooded system. The need is to reconsider our planning, make sure that any new developments are above maximum probable flood level. That's maximum probable flood level now. What it is going to be in the future, who knows? And as long as we've got governments that continue to promote the coal industry and burning of fossil fuels, which we seem to have in Australia still, then we can only see the situation getting worse. Insurance costs are going through the roof. Some people can't even get insurance at all now because of where they're located. So we need to have a real good look at where people are living now and maybe move them on. I think one of the solutions is that as humans, with our ever-growing population, we're going to have to accept that we're going to have to live in high-rise. We need more ground space to cater for water flows and I guess green space to try and limit the urban heat island effect and all of these others. So it's a very big question. As far as costs, I'm a cynical person. I think it would probably be probably about as much as a fleet of nuclear-powered submarines, and we just got to get our priorities right.
Thank you for that, Colin. And I just want to stay with you for this next question that's coming from Micah in Victoria, asking you, Colin, can you comment on permeable paving / porous paving, as well as stormwater infiltration systems to support tree growth? Colin.
Yes, I've installed a number of permeable paving options around Perth. I've used the no fines concrete pavers with good effect. In a lot of Perth, we've got free draining sands underneath. So once the water gets through the paver, as long as you select your base for those brick pavers correctly, you can get the water to keep going vertically down into the sand system and get rid of your water without much issue. Because over east, we've got black soil areas and heavy clays, and we do have some heavy clay areas in Perth too. In those sort of situations, you do need a subsoil system to get rid of the water that accumulates in those permeable paved areas. Many of the tree species that we would plant in tree gardens, for example, don't like permanently wet feet. So you do need a tree growth medium, but you need to drain that with a subsoil system of some sort. It's important when you do build a subsoil system, though, that it is maintainable. And for that reason, I prefer circular pipes that one can get a root cutter up and root cut those drains or de-silt them if they silt up. The other systems, of course, are the under road systems that you can drain in, whatever catch pit system you use. The inverted arch systems I've found have been very successful around Perth. You can use those as either detention systems or retention systems and contain the stormwater systems or the stormwater much closer to the source. So I hope that answers the question.
Thank you, Colin. Thank you. And Darren, coming back to you, a question that's come in from Sobranium in New South Wales. Good afternoon to you. Asking you, Darren, in pedestrianised zones, how do we manage the surface water to drain using eco products? Darren.
Thanks, cmcmennemin. Yeah, with using eco products, putting it into a design, it also got to be designed well with the pavement. Pavement design is very critical, especially in flat pavements. Flat pavement, you're trying to direct the water to the drainage system. So in flat areas, the best way is put a trench drain along a valley, and then you have the both sides of the drain with a crossfall, gentle crossfall, directing the water into the trench drain. Also, you need to hook into existing stormwater. With a lot of these shared spaces now, they potentially were a road before, so there is existing drainage that probably runs along both sides of the pavement there, and then your drainage there to hook into the existing drainage. You don't want to introduce as many more pipes. Use the bare minimum to change that space. Also, the grates, with the grates, the optics are also important. So the aesthetics, what it looks like, and then with that, it's more probably the concern of the landscape architect. So talking to the landscape architect to understand what the look they want for the area, and then selecting a grate that meets the load class, meets the hill safe requirements, slot criteria requirements for that area is very important. I suppose with these big pavements, you want to redirect it into possibly a retention or a detention system or infiltration system, and ACO also has the storm brick system that can help out with that.
Thank you for that. Colin, we've had a question come in from Nadia from Canberra asking you, how can we reduce the carbon footprint in stormwater surface treatments? Thank you, Colin.
Well, I guess one way is to look at your materials. If, for example, we look at the pipe networks, you look at concrete pipes, they're very heavy, they have thick walls, and although its production per unit weight of around about 0.92 kilograms per kilogram of concrete, as far as CO2 equivalent goes, is a little bit lower than what plastic pipes are, which are 1.5 kilograms of CO2 per kilogram equivalent. The weight of the concrete pipes means that we're generating a lot more CO2 per metre. And if you look at, say, 100 metres of 450 mil concrete pipe, with the weight of the concrete pipes, you've got about 18.75 tonnes of CO2 equivalent. Whereas with the lightweight plastic pipes and being more flow efficient for a 450, you can reduce it down to a 375 corrugated PE pipe, for example. You're looking at about 1.2 tonnes of CO2 equivalent per that 100 metres. So selection of materials helps. If you specifically want to use concrete pipes, maybe we should be encouraging companies that use geopolymer concrete more in the manufacture of their pipes than Portland cement. And of course, one of the other ways we can do it is avoidance. And I go back to people living in high-rise. If we had people living in high-rise, maybe we could have more living streams to dispose of storm water rather than pipe networks. And that way we're using natural drainage channels and we're creating habitat at the same time, which we humans seem to be masters at reducing for other species at an alarming rate. So that's my answer to that question.
Thank you, Colin. Darren, we've had a question coming from Christopher watching in New South Wales, asking you, Darren, are there high quality finished products, for example, stainless steel, that can meet higher load class requirements, e.g. class C and D? Darren.
Thanks, Chris, for your question. For road drainage, obviously iron is the most durable product. You can, as Colin alluded to in his presentation about iron covers in roads, if iron can last a long time in roadways. So iron can be used is very strong and is a durable solution for roads. As for shared spaces, there are heavier duty materials that can be made into grades. Stainless steel, depending on the design, you can make the structure a lot stronger to cater for heavier loads. But obviously, with stainless steel, it's a softer material, so you probably want to use stainless steel in areas where there is not frequent traffic, just the occasional heavy vehicle going over it. Then I think stainless steel will be okay. But in highly trafficked areas, you wouldn't use stainless steel, especially in roadways. But in pedestrian areas, landscape architects like a nice shiny grate, and stainless steel is very commonly used. There are Class B grades. They can be further strengthened to Class C and Class D. And ACO here, where we're about to release a Class D grate in the near future. So just look out, and that'll be rated to Class D 240, and it'll meet the slip resistance, hill safe requirements.
Thank you, Darren. And just staying with you for now, we've had a question coming from Chan asking you, Darren, cost comparison between curb drain versus traditional curb in terms of construction. Darren.
Thanks for the question. If we just look at the curb drain and versus traditional curb and the cost in construction, obviously curb drain would be a lot more expensive versus traditional curb, but you've got to look at the total drainage solution. So if, for example, when we discussed the road drainage with closely spaced pits, if we're using closely spaced pits with underground pipe work and and in between the pits are just traditional curbs, you're looking at a big difference in cost, because with the curb drain, it's so shallow, the excavation, there's no deep pipe work. So with our little cost comparison that we discussed in my presentation, with the curb drain installation, it was actually about 15-16% cheaper than the curb inlet pit and pipe system, because of the with the curb inlet pit and pipe system, you've got to pay for the actual products, the curb inlet pits and also the pipes, along with the curbs. Whereas if you're just installing a curb drain system, you're looking at the overall cost, you're just looking at the excavation of that trench and then the actual curb drain and the concrete that goes around it. So if you look at that in that perspective, the curb drain drainage system overall is a lot more cost effective than looking at a traditional curb inlet pit pipe system with standard traditional curbs.
Thanks, Darren. Thank you. Colin, we've had a question coming in from David in Victoria, who's talking about street litter, asking you, Colin, how can stormwater systems be designed to deal with street litter to prevent blocking as well as pollution of downstream waterways? Thanks, Colin.
Okay, well, we have to accept that we do need to remove surface water from roads, and often there's no overflow or no overland flow route, and that's often due to poor subdivision design in the first place. So when that litter blocks gullies, then ideally we'd have an overland flow system, and this also, I guess, goes back to the previous question about designing for floods. We should have an overland flow path designed into a subdivision design, so that when the stormwater system is surcharged, it doesn't go into properties, it goes an overland route somewhere to a watercourse. But there will be debris, unfortunately, as I said before. We humans are not the high form of life that we think we are. When you look at the litter and junk that we chuck around on the road system, and that gets caught up into the stormwater system. So we can have individual traps at gullies, and that's probably the first and foremost that we should be doing. Well, no, before that, as I mentioned before, street sweeping. The more regularly we do street sweeping, the less is going to get caught up into the stormwater system. And that's the best solution for getting rid of that litter in the first place. But once it gets into the system, certainly at the gully, the more we can do at the catch pit, the less that gets down into the system. But we do need to be wary of blockages, and then we go down to the next step, which is the gross pollutant traps. The gross pollutant traps generally have a bypass system for high flows, and the traditional theory is that if you look after the small event, the 1 in 3 or 1 in 4 month event, that most of the litter you'll catch, because you get a lot of low intensity storms compared to the occasional high intensity storm. So if you can catch most of the flow in those low intensity events and filter out the litter, and have a bypass system for those major events, then you will control a lot of that litter that gets down into the stormwater system. Obviously, the graded gullies are going to be more effective in keeping the litter out than side entry gullies. That's why having traps within the individual gullies, or the filter fabric within the individual gullies can be effective. But again, they need regular maintenance, and quite often we're not that great about about maintenance of these systems. The other option, of course, is to have the retention systems with a constructed wetland where you have an inlet bay which traps most of the urban litter, and they can be quite effective because we've got one in a high intensity commercial area in the city of Canning where that initial sediment bay can display to people exactly how dirty we humans can be. And you've got all of this litter in high visibility location, which hopefully might affect some people in reducing what they chuck away. So hope that answers the question.
Thank you, Colin. Thank you. Darren, we've had a question come in from Ken. Good afternoon to you, asking, Darren, are there any maintenance issues of adopting graded trench drain or curb drain, i.e. frequent cleanup required to avoid debris collected at the inlets?
Thanks, Ken, for the question. So this is pretty much, Colin just answered this question. In regards to maintenance of graded trench drain and curb drain, it's the same issue. With graded trench drains, what we tried to develop with the actual Department of Transport in New South Wales was we developed a high flow grade. What they found was that with the designers, they'd rather have the debris fall into the channel than have it on top of the grate. So if we had small slotted grates, debris will collect faster and it will block up quicker. So what will happen is then your drain is not functional. The water will spread out onto the road because there's blockage in the grates, and then it'll become a hazard to motorists. So to overcome this, we developed a grate, our high flow grate. One of the requirements was the high flow grate would allow a Coke can to fall through. So that's why the slots are that big. Their theory was to have that debris in the channel, and hopefully during the intense storms and the high flows, it'll wash it down into the channel. The channel will wash it away, hopefully to a gross pollutant trap, which is also needs to be maintained as Colin discussed before. So we've also with the curb drain, same issues. Very low flows, the water, the stuff will get collected along the curb. Then during the flows, hopefully gets washed in. And the high flows, that the channel will get cleaned out. With the curb drain, with the inlet slots, and with the high flow, as I showed in my presentation, they can be cleaned without removing the grate. We actually, for a project in New South Wales, a condition was the Department of Transport want to see that it can be cleaned out. So we invited the road authority out to our facilities out at Western Sydney here. We actually got a trench drain in our car park. We filled it up with sand, and then we got a sucker truck in, and then we just demonstrated that you don't have to remove the grate to get rid of all the debris. So that was a contingency. This project was on a very a road that leads to an airport, so they didn't want to shut it down to clean the system. So they tried to minimise the maintenance time. So that was one of the conditions. So maintenance is an issue with all drainage, from time to time, everything needs to be maintained, and drainage is part of it too.
Thank you for that. And as always, we are running to the end of the session, and I want to say a big thank you to everybody that participated in the poll. And the results have come through, and we will share them with you in the post-event EDM after the webinar. Darren, starting with you, do you have any comments on the results?
Look, the results are very interesting. The first question about inlet sizes, with the Australian standards, there is nothing that specifies what hill safe is. So even in regards to the poll, at 41% was 10 millimetres, and 8 millimetres we had 39%. So they were the two major ones, and that's pretty much what we consider as hill safe, and that's how we sort of market our grades as hill safe anti-slip with 10 millimetres or less. But then, we have got slot sizes that are less than 10 millimetres, 8 millimetres, even down to 6 millimetres. With the curbside gutter question, the continuous channels with removable grates was 68%. So that was the preference for most of you. Curbed profile was 22%. And then we're looking at what we can supply as a from a drainage supplier, and obviously hydraulic services, any download sheets. So they're all pretty important. They're all pretty even. So thanks for participating in that poll. It gives us a lot of insight on what the market requires, and with the and what products we should design for the market, and what services that we can provide to help you.
Colin, do you want to comment on the poll, or are you all good?
No, I'm all good. It's more applicable to Darren in the manufacturing industry. I don't manufacture drains, so that's more Darren's area.
Okay, so just to finish up, I'd just like to invite you both, and starting with you, Colin, to just, we've discussed today a lot, surface drainage, roads and pedestrianised shared zones. So it's a big topic, a lot happening. It is very topical. You can tell that by the number of registrations for this event. So Colin, what are you, say, 3 main takeouts from your presentation you'd like to leave our audience with today?
My 3 takeouts are to be more considerate of the environment, where the stormwater goes to, and make sure that we clean up our act as much as possible. Try and get away from pipe systems as much as we can, and create more overland flow paths with living streams that can create more habitat. And I think we've just got to recognise that as humans, we can't keep living in ever-increasing single-storey dwellings with 400 square metres in each house. We need to start living high-rise and leave more open space around for less paved areas and less runoff.
Thank you, Colin. Darren.
Yeah, just with I suppose road drainage, especially in flat areas and where there's issues with existing services, please consider continuous capture inlets like the graded trench drain or curb drain as an option. These could help. These are problem-solving solutions, so consider that. In regards to shared spaces, look at specifying hill safe anti-slip grates in those kind of areas, and consider ACO. If you need any of your drainage or services, we're here to help you specify the correct station.
Thank you for that to both of you. And we have talked a lot about the environment, and it's been such an interesting session today. And I want to really warmly thank both our speakers. Just a reminder that Engineers Australia's flagship event, the Climate Smart Engineering Conference, is in November this year, the end of November. So if you jump on our website, and really recommend that you have a look at attending, as we know it will be engineers that are providers of many of the solutions for the challenges that are coming. It's all we have time for today. Once again, thank you to Colin Leake and Darren Chan for their time. I'd also like to thank Engineers Australia's industry partner, ECHO, for their support. As always, we're looking for ways to improve and plan. So if you could take 2 minutes to complete the short feedback form, which is linked in the description box below. Thank you again for joining us this afternoon, and I look forward to seeing you at a future Thought Leaders event. Thank you.